Dear students, today we will be talking about the force and pressure chapter in short. So, force, it is a pull or push exerted on the body, that is called force, and push or pull on a body. Now, the SI unit of force is Newton, and CGS unit is Dime. Correct? And 1 Newton is equal to 10 to the power 5 Dime. Now, weight is also a type of force. So this is Earth, this is the center of the Earth, a man is standing over here. So the center of the Earth is pulling the man towards itself with some force. That force itself is called force of gravity, or it is also called weight. Correct? So the SI unit of weight is also Newton. Now we have another force unit which is called 1 kgf. Now 1 kgf means it is the force exerted by the earth on 1 kilogram object. So that means weight of 1 kilogram object, that is given by mg. M is 1 kilogram, g is approximately 10 meter per second square. So this turns out to be 1 into 10, that is 10 kg meter per second square is Newton. So 10 Newton is the weight of 1 kilogram mass object. Right, and this itself is called 1 kgf. So 1 kgf is the force exerted or the weight of 1 kilogram object. So 1 kilogram force, 1 kgf is equal to 10 Newton. This is the conventional unit of force. Right, now let us talk about the effects of forces. Effect of force, that is the turning effect. Rest all we don't need to discuss over here. So suppose we have a nut bolt like this, and this is a spanner. Correct? So the distance from here, center of the bolt, to the edge, this point, this distance is r. You can also call this as a length of the spanner from the center of the bolt till the edge of the spanner. Now I am going to exert force, say in upward direction like this. So I am exerting force F. Now due to this bolt is going to turn. So there is a turning effect produced over here, and that turning effect is called torque. It is called torque or moment of force. Now there are two sub cases over here. Like in this case, if I pull out, assume this to be the length, and this length vector and this F are at an angle 90 degree. So torque is equal to simple R into F. Now this SI unit of torque is, this distance is in meter, this is in Newton. So Newton into meter is the SI unit of torque. Correct? So I may want to underline with the another color pen. But what happens if you have another case, something like this? Suppose this is the spanner, same again over here. Now I am exerting force like this. This is again R from the center of the bolt to the edge of the spanner. Now if I pull them, the angle between them is theta. So in this particular case, torque is equal to R F sine theta. Sine theta does not have any unit. You will be given the values of R, F. If angle theta is given, then sine theta will also be given to you. Just multiply all of them and final answer would be Newton into meter. Now next part is pressure. So pressure is P is F by A. This is the formula for pressure. So if I make this as 1 meter square, then P and F will become equal, which means pressure is the force exerted per or on unit area. Unit area means 1 meter square area, correct? So whatever force you are exerting it on 1 meter square object, that force itself will become pressure. And the SI unit, since pressure is equal to force upon area, so force is Newton, this area is meter square, so pressure is Newton per meter square, or it is also called Pascal. We speak pascals, but we say Pascal, and it is also written as capital P and small a, right? Okay, now we can see two things from here. Number one, if area is increased, then pressure will decrease because pressure and area are inversely proportional. Second thing, by keeping the area constant, if you increase the force, then pressure will increase. These are directly proportional. So area increase, pressure decrease. Force increase, pressure increase. Right? And if I say that, suppose 1 Newton is the force applied on 1 meter square area, then 1 by 1 is 1. Newton per meter square is Pascal. So 1 Pascal is the force exerted. 1 Newton, when 1 Newton force is exerted on 1 meter square area, the pressure itself is called 1 Pascal. Now, what are the applications of pressure? Suppose we have a horse and a camel. So we know that the feet of the horse are smaller and they have small area, of course, and the area of the feet of the camel is comparatively larger. So A large and this is A small, correct? So we know that the pressure is inversely proportional to the area. So the pressure exerted by the whole body of the camel on the foot will be very large because area is small. So more the pressure, more the foot of the horse is going to go inside. Suppose they are running in a sand, correct? And less is the pressure because area is large, so the foot of the camel is going to go less deep inside the sand if they are running in a desert together, right? So these kind of questions. Another thing that you might be recalling, if you want to cut a vegetable with a sharp knife and a blunt knife. So blunt knife are comparatively they have larger area. Exert force, this is blunt knife, this is sharp knife. So the area is small, area is large, pressure would be small, pressure would be large. More the pressure, more it is going to go inside the vegetable and the vegetables will be cut very easily, right? Okay, now you may be asked these kind of questions, that suppose a man is standing and the area of the feet is given to you and find the pressure. So pressure is equal to force upon area. Now you might be wondering, there is no force, but remember the weight of the man itself will behave like a force. So that you are going to substitute over here, area will be given and final answer in Newton per meter square or Pascal, correct? This is in short. Now next one, you have liquid pressure. This is very important topic. Now suppose this is a vessel and the liquid is filled till here. Another vessel is like this. Again the liquid is filled till here. Now we need to understand what is depth. So this is called free surface. This part the top surface of the liquid which is in contact with the air, it is called free surface. Now from free surface to the bottom is called depth. Suppose this is depth. So if I measure the depth from here, I would be getting the same answer, right? Assuming that water is over here and water is over here, then the density of water is rho W. Depth is same for both of them. Then pressure exerted by the liquid at the bottom is equal to H rho G. Now H is same for both, rho is same for both, G is same for both. So the pressure exerted by the liquid at this point and at this point is same. So the area of the vessel doesn't matter, the shape of the vessel doesn't matter, size of the vessel doesn't matter. So the pressure exerted by liquid only depends upon depth, rho, that is the density of liquid, and G. So suppose if I calculate pressure here at this point and pressure here, that means here the depth is more, depth is less. More the depth, more is the pressure, correct? And pressure itself is a scalar quantity. It does not have any direction. That means it is in all direction. So the liquid exerts pressure on the walls also, pressure on the top also, pressure at the bottom also. In all directions it applies the pressure, right? So liquid pressure is independent of volume, shape, size of the container, and we will understand this one by one. So we have a container over here, say for example a small bottle like this, completely filled with water, and now I'm making two holes over here, one hole over here, another hole over here. Now this is the free surface, top part of the liquid. So from here this is at a depth say H1, and from here say for example this is at a depth H2. So if I give you 2 points A and B, then the pressure at B would be more than pressure at A because liquid is same, G is same, so density is same, and H is more over here, so pressure is more. So from here the liquid is going to go till here, whereas the liquid is going to go till here, correct? Now another thing, that if I give you two identical containers and if I say that, say kerosene is filled in this and water is filled in this, but the depth are same till the bottom. So here in this case pressure is equal to H rho G and the density of kerosene is say less than that of the water, then the pressure exerted by kerosene at the bottom would be less, correct? This is in general discussion about the pressure. Very important thing you should understand is that pressure exerted by the liquid is independent of the shape, size of the vessel, correct? Okay, now what do you mean by manometer? See, manometer is a U-shaped tube, something like this. Now if you fill, say for example this with mercury from one side or the other, both are open ends, this is U-shaped tube, it doesn't matter. So it will be filled till here, suppose here. So the liquid attains a common level. So now this is mercury level in both the arms. Now this is itself called a manometer. What is its use? So what we are going to do is we are going to put a small flexible pipe over here, then I'm going to cut a ball into half, and that ball I'm going to put it over here by making a hole over here, then I'm going to tie a balloon over here like this. This is our manometer ready. Now what is it is used for? So suppose you have a vessel like this and the liquid is filled till here, correct? This is your U-shaped manometer. Like this, and here there is a scale in which the readings would be written our normal scale only. Now what is going to happen, this is mercury, and this pipe, you put it inside water like this. Now the water is going to exert pressure like this in the upward direction. If you put it like this one, then the water is going to exert pressure like this. That is called lateral pressure, the sidewise pressure. Correct? Then also it does not matter if you keep it like this or if you keep it like this, even if you turn it like this, or if you even keep it up like this one, it is not going to matter. As long as you are maintaining a constant depth, the pressure is not going to change. So our main purpose is to find the pressure exerted by the water at this depth, and that pressure would be equal to, now what is going to happen is the water is going to exert pressure. Here there is air, so there would be an extra pressure felt by the air on the other side. So what is going to happen is the mercury level here is going to go down and the mercury level here is going to go up. So finally you would be seeing something like this. On one side the mercury level goes down, on the other side the mercury level goes up. Now this is H. So this pressure exerted by the water over here, I'm sorry, cut off this H. This H is the height difference of free surface to free surface of the mercury, right? So pressure exerted by water is equal to height difference multiplied by the liquid filled over here, which is mercury, and the density of mercury is, say, rho Hg multiplied by G. Just remember this, nothing else. So if you insert this more inside the water, pressure increases. So this still goes down, this still goes up, right? Okay, and this is manometer used to measure liquid pressure, right? Now we have Pascal's law. Which states that liquid transmits pressure applied on it equally in all directions, and that too without getting diminished, right? So this pressure doesn't get decreased when it passes in the other direction. So in our textbook a very simple activity is given. So you have a ball which is, say, filled with water, and there are very small holes like this, and when you apply force, so that force turns into pressure, and due to which the pressure is created inside, and due to that pressure the water comes out, and this water comes out with equal pressure. And how do we check that? So their speeds would be equal. So that is one way of checking it. Actually it is not a very good example, but this is enough for you to learn during exams, correct? So when you exert force, it becomes pressure. Now that pressure is equally transmitted to all parts of the liquids, and finally the liquid comes out with equal pressure and with equal speed. This is Pascal's law, and its application is hydraulic jack. So this is something called hydraulic jack. This is piston having smaller area, A small. This is piston having bigger area, AB, and this is filled with oil or any other liquid. you apply force F. So force F divided by AS is the pressure created in the liquid, and now that pressure is going to get transmitted in all directions, like this, like this, like this, like this, over here. And finally this pressure is going to push this in the upward direction, right? So this pressure is P again. The same pressure which was produced over here gets transmitted without getting diminished in all directions. That is pressure P, and P multiplied by AB would be the new force acting in the upward direction. This is the use of the Pascal's law over here. Now we would be talking about the air pressure. So this is Earth, and Earth is surrounded by the layer of gases, and gases all are made up of atoms. So when we are standing on the Earth, we are being hit from all sides by these atoms. So the force exerted by these atoms divided by the part of the body area, that is called atmospheric pressure, right? And that is generally represented by PA, that is atmospheric pressure. Now what happens is, suppose this is a mountain, and as you go up, the molecules would be found very less. So it is because the acceleration due to gravity decreases as we go up. So the pull by the earth on these molecules becomes lesser and lesser. So these molecules at the top of the say top of the mountains can escape very easily from the earth surface pull. So as we go up, the air becomes thinner. So if a person is standing over here, too many molecules are going to hit this man, so the air pressure is larger over here. But if we stand at the, say for example on Mount Everest, there is very little amount of air, so less amount of molecules are going to hit us, so the air pressure is less. Correct. This is very brief introduction about the air pressure. At sea level, the air pressure value is 101.3 kilopascal. That means 101,300. Kilo means 1000. 1 stands 100, like, okay. So this is the value over here, 1, 2 and 3. Okay, I'm done, right? So this is the atmospheric pressure value at the sea level. And now how do we measure this? So atmospheric pressure can be measured with the help of an instrument called barometer, right? So barometer is something like this. You need to take 100 centimeter long test tube completely filled with mercury. Make sure there are no air bubbles. Take another vessel which is half filled with mercury. Put your thumb over here gently. Invert this test tube. Put it over here. Like this. Now, what is the situation in front of us? There are 2 points A and B. This is point A and this is point B. So this mercury has got depth H from the top. We know that is 100 centimeters. So pressure exerted by this at point B is H rho of mercury into G, and this pressure at A is pressure exerted by the atmosphere, that is PA. So initially PB is greater than PA, so the pressure at B is more than pressure at A, so this liquid mercury will come out. So the level of mercury will start falling inside, and finally it will stick at 76 centimeters, something like this. this depth is 76 centimeters, and then no mercury comes out nor this mercury goes in. That means the pressure at these 2 points A and B are now balanced, correct? So pressure at A is now equal to pressure at B, which is equal to H rho G, and pressure at A, that is equal to new depth of the mercury is now 76 centimeter, so 0.76 meter. This is 13600 kg per meter cube, multiply by G, that is 10 meter per second square, and we are measuring this atmospheric pressure in this way, correct? Okay, so if you are using, say, a very heavy liquid, then heavy liquid shorter column is going to balance the air pressure. But if you take a very lighter liquid, then it is going to, you need to take a longer amount of, or longer height, or more depth is required in order to balance that air pressure, because denser the liquid, lesser the column, and less denser the liquid, then you are supposed to take more amount of liquid. Now the applications of atmospheric pressure. So we have typical example of syringe, or if you are, say, drinking, say this is water, and you have a straw which is inside like this. Here is air pressure acting, but the problem is this straw is also filled with air. Now we put our mouth over here and we suck all this air out. So when you suck this air out, what happens before sucking this air is pushing the water down, so the water wants to climb up, but this air pressure is not allowing this water to climb up. So the problem is, if we remove this air, then our problem would be solved. So if I suck this air out, there is no air over here, so there is no one to stop this liquid from rising up. So this air pressure is going to push the water, and finally the liquid is going to go up in the container, right? And sorry, in the straw, and finally comes inside our mouth. Same thing, you cannot drink this water with the help of straw or coconut water, whatever it is, in the moon, because in the moon there is no atmospheric pressure, so there is no one to push in this direction, so the liquid cannot go inside the straw, right? Another experiment, what you can do is, you can take a Coca-Cola can. This Coca-Cola can, fill it, some of it with water. Now initially it was with air, so this part is still